Yeah, before we move on and talk about the multi-class example of logistic regression, the so-called softmax regression, let's just wrap up everything we talked about in the previous 4 videos in a code example. So I prepared a code notebook. You can find it on GitHub. I will share the link on Canvas, where I have implemented 2 things. So the first thing is logistic regression from scratch, just from the ground up. A low-level implementation of logistic regression, really like implementing the learning rule that we talked about here. And then I will show you how we can do that using the PyTorch utilities, the module API that we talked about last week, where we have this nn.linear layer and so forth. This is something we would do in practice when we have, of course, more complicated networks, but I thought the from scratch implementation is still useful from a learning perspective, so you get a better feeling of how logistic regression works. So let's get started. So, of course, first my watermark. You can ignore the Torch version. This Torch version doesn't exist, actually. I yesterday compiled Torch from source to test something, so this should also work on Torch 1.7, so no worries, can ignore that. So then the import of matplotlib, which we'll be using, NumPy we will be using, and then the Torch stuff we will be using. So just some imports to get them out of the way. We will be using some simple toy data set. That's like, I think that is what I gave you also for the homework, to be honest. I have to double check, I made multiple of these toy data sets. Yeah, that's just a simple binary classification data set. Now here is my logistic regression implementation. So how does it work? So I'm using the roughly same way how we would implement that using PyTorch with a module API. So here I'm implementing forward and backward manually. These are the 2 methods, where forward is the forward pass and backward is the gradient descent, computing the gradients of the loss function. Let me modify this. Let's call that loss with respect to. So WRT means with respect to. I think it makes it clearer. So that's the gradient of the loss with respect to the output and so forth. We'll just modify it everywhere here. All right. And then let's do it step by step here. So then here in the init function, this is like the function or method that gets executed when we instantiate a new object from this class. What we have is the weights and the bias unit. So the weights, we initialize them to zeros. So we use the zeros function to initialize them to zeros. It's a vector, it's a row vector, basically, a 1 times num features vector, or matrix. So it's essentially a row vector. So num features is the number of features in the data set. So the number of weights is equal to the number of features, just like in Adeline. And we only have 1 bias unit. All right, so the forward method, this is computing the net input, right? So this is the net input. You can also call it Z. We could technically call it net input, but you know what we mean, right? I mean, I can rewrite this, maybe. Doesn't really matter. Well, I can just leave it like that. I think I'm underestimating you. I think it's probably all clear to you. I don't have to use these different words. All right. Sorry. So the backward method is, computing these gradient terms. This is going back to what we've done here. So here I'm computing the gradient of the loss with respect to the output. So this is essentially this part here. Then the gradient of the loss with respect to the weights. This is this part here, where I put those 2 things together. So this should probably be with respect to Z, the net input. It's maybe clearer instead of saying output. So this is matrix multiplication between X and this term. I just rearranged that to make the dimensions match, which is why I have the transpose. You, to be honest, don't have to memorize these details. You will probably find out by tinkering with the code. If you ever implement something from scratch, because here this is really for one weight, and here I have that as a vector implementation for multiple weights, right? Because we have the number of weights equal to the number of features. It's a little bit more complicated, but the concept is the same. So this line here really is this part here. I can actually also maybe go to this part here. So this part here, this is essentially this one here, the gradient of the loss with respect to the weight. And then the same for the bias, which would correspond to this part here. Here, this is the threshold function, predict labels. So I'm calling forward. That gives me the probabilities, A. So A is the probabilities, probas. I call them probas because in the lecture I said also it was a little bit complicated when we had y hat, and it was confusing. So I refer to A as the probabilities. That's the sigmoid activation here. And this is the threshold function, where if the probabilities are greater than 0.5, return class label 1, otherwise return class label 0. I could, however, also do it as with the net inputs. I could say if the net inputs are, let's call them 0, are greater than 0, then return 1, otherwise 0. This is because what we discussed here. So here's the threshold function. And because the probabilities, if they are 0.5, the net input is 0. So either we can operate directly on the net input or the probabilities here. So you have that with the probabilities, but doesn't really matter that much. Okay, so here's just an evaluation function. So this is not super interesting. Here I'm predicting the labels, which in turn uses this method here, which computes forward, and then the threshold function here. So we can call it the threshold function. And then in order to compute the accuracy, we sum over the correct predictions. So every time the class label matches the predicted labels here, matches the actual class labels, every time they match, we sum that up. So this is the number of correct predictions, and then divide by the size of the training set. So it's a value between 0 and 1. It's the proportion of correct predictions. Why do I do float here? It's because the class labels are integers. And yeah, in PyTorch, it's a little bit tricky to compute or compare things like floats. The labels are floats here. And then this is integer. I think I could have omitted this here. It's maybe a little bit complicated. I could have also done that, and it would also have the same effect. So, but anyways. Okay, anything else? Yeah, this is a sigmoid function, which you have seen a lot of times. So this is this function here. Yeah, the loss function, that's the negative log likelihood, which we have right here at the bottom. That's the logistic cost function. And here's the training function. So here, again, let me jump back to this one. We are right here now. So for every training epoch, for E in the number of epochs, we compute the outputs, which is here. That's the probabilities, the A's. So this is really, this should be an A actually. So remember, this was copied from the adder line. Should have probably adjusted it to an A here, but you probably know what I mean. Then we compute the gradients. So these are under B here. Then we update the weights, which is C, this part here. And this is it. And this is just for, yeah, logging, just keeping track of everything, like looking at the results and the loss curve, which can be useful. So let's actually do that. Let's do that here. What I'm doing is I'm converting the NumPy arrays to torch tensors, because if you go up here, you can see I used NumPy here. So to load the data. So here I'm just converting them to torch tensors. Then I'm initializing my logistic regression model. So this will be actually step 1, initializing. And then I'm calling train. Train would be everything under 2 here. And then I'm printing the model parameters, the weights and the bias, just to take a look at them. And I'm training for 30 epochs with a learning rate of 0.1. So I think that's the mistake I always make. I talk through this, but I usually forget to execute this. Okay, now we are running the code. Okay, we got an error here. Okay, I changed the name. 1 second, let me fix that. Let's call it Z. All right, so it's training. You can see it's blazing fast. It starts with already a very high accuracy after the first epoch, to be honest. So it's it's actually training super fast. The cost is very low, but you can see if I do more epochs, it goes even lower. The accuracy goes up to 100% here even. But you can see even though the training accuracy is already 100%, the loss still goes down. I could have trained more, it would go maybe down further, but that at that point might not be necessary, might be overfitting. All right, I wanted to execute this part. Okay, there's some message here. I think this message comes from NumPy because I recently installed a very recent version of NumPy, and it must be something in Matplotlib here. You can actually ignore that this is not error message, that is just a warning. So if you see warning or deprecation warning, that means things are still working, so don't worry about them. But in future, if there's an even newer version of a software library in Python, this may not work anymore. So here, this is nothing we are doing wrong. This is probably something inside Matplotlib, and I'm sure they are already aware and working on that. So don't worry about this warning. Everything still works fine. There will be probably a new Matplotlib version that addresses this issue at some point, but everything is fine. You can see here is how the negative log likelihood loss looks like. So it should be the negative log likelihood loss to be precise, and then over the number of epochs. You can see maybe it will go down further. You can see it's actually going steep down, but whether it's actually helping, I don't know, because we already get 100% training accuracy. So let's take a look at the test set accuracy. It's only 96%. For completeness, we will also take a look at at this here. So we can see actually here on the training set, the decision model looks quite good. So it's dividing both classes, class 0 and class 1. On the test set, it's not performing so well because there's this one outlier point, right? So here, this one is not classified correctly. So if this decision boundary would go a little bit more to the right, then we might get this one correct. But at this point, this model only sees the training data. It doesn't know of this point here on the right-hand side. So in this case, I think training the model further wouldn't really help because this is already doing a good job here, actually. Maybe putting it a little bit more to the right would help, actually, because then it would be more here. Yeah. Anyways, this is just an example, of course. I just implemented this quickly in a way that I didn't really fine-tune anything. And this is a toy data set anyway, so don't overinterpret this. Okay, so the goal here was really to show you, if I scroll up again, to show you how we implement this from scratch. Like the most interesting part, I would say, is this backward function, which is a little bit different from the add-a-line function. The rest should be all the same as in the add-a-line implementation, so it's not that new to you, I hope. Now, I want to show you though how we use the module API to implement this logistic regression model here. So here, this should do exactly the same thing, but now I'm relying on inbuilt or built-in PyTorch functions. So I'm using this self.linear here to refer to my torch.nn.linear layer. This is a layer that computes the net input. However, note that by default, this will initialize the weights to small random numbers. Later on, this will be very useful, but it is not that useful to compare it to our model above, because if you recall, above I initialized my weights and bias to 0. So I want to do the same here so I can compare the two models. So what I'm doing is manually assigning zeros to the weights and bias unit. And then we have the forward method. So here, the forward method, we compute the logits via the self.linear, which is this fully connected layer or linear layer. And then we have a built-in PyTorch function that computes the sigmoid activation function. So you can see a logistic regression model is actually super simple. Actually, we can also, it would train just fine if we have this one. just for comparison reasons I have this one, but you can see how simple it is, and it will already implement the backward function for us. We don't have to do it ourselves. Here we are using the stochastic gradient descent optimizer, so this will update the weights then. So this will compute the gradients via the backward and update the weights. So we are just specifying what weights we want to train. This is the model parameters here, model 2. So this is model 2, or logistic regression model 2. Model 1 was the from scratch implementation. All right, so here is just an accuracy function to compute the prediction accuracy. We are training also for 30 epochs. Like before, what I'm doing is I'm casting the NumPy arrays to a tensor. I've already done that, so it's pretty redundant. And now here's my training loop in PyTorch. So for each epoch, I compute the outputs. These are the probabilities. This is from the forward pass. This is these probabilities here. Then I use this cross-entropy, binary cross-entropy function. And this is essentially why I spent some time in the last lecture, last video here, when we had this topic here, why I spent some time just telling you that the negative log likelihood and binary cross-entropy are equivalent, same thing. Here I'm saying reduction sum because that's what we have done here. It's a sum, but we can also do the average. Actually, if I change this, it will be the average or mean by the default. But since we implemented above the sum too, when I have the sum here, I'm also, for comparison reasons, use the sum here. In practice, I think using the mean is more stable for with regard to learning rates and different batch sizes. And then this is really like what we've done in the last week when we trained Adeline using these automatic things. We have the following. We compute the loss. I traditionally use the term cost, but I think loss is more natural nowadays. Then we set the optimizer 0 grad, which will reset the gradients from the previous round, otherwise the gradients will accumulate, like I explained last week. And then we compute the gradients for the current round, and then update the weights. And this is essentially it. Let's run this. All right, error. Model 2 is not defined. See, I always forget to execute things. All right, let's execute this one and then this one. Yeah, it trains. Okay. So then you can see, if you recall, these have the same values as we've seen before. I can just scroll up in a second and just to show you. And also take a look at these weight parameters. You can just copy and paste them. So yeah, you can see they're exactly the same. So we learned exactly the same using PyTorch, which gives us confidence, I hope, that we understand gradient descent correctly and implemented the gradient here correctly. So it's the same as in PyTorch. All right. And this is it essentially. So evaluating the model, same tested accuracy, because it's the same weights and bias, so it should be the same decision boundary, which we can see here. Yeah, so this is how we implement logistic regression. I hope that was helpful, like understanding a little bit better how these different concepts here in the slides work. You may also want to work through this more slowly. I think that might be also helpful, but yeah, that's it. So in the next video, we will then talk about how we can generalize these concepts to multiple classes. That means like more than 2 classes.